All right, so in this video, we are going to be deriving the D5 character table. And this is an interesting one, a fun one. Anytime you have C5s, 72-degree rotation, points of symmetry in your molecule, the math gets pretty crazy. I think when you're first learning this sort of character table business, you think everything is ones and negative ones, symmetric and anti-symmetric. What happens if you have a character of cosine 2 pi over 5? We're gonna have that in this example. So there aren't many examples of molecules in this point group. It is chiral, but I wouldn't even bother trying to visualize this. What I would think about instead is D5H, right? So D5H, example of a D5H molecule is some sort of pentagon shape. And of course, in D5H, you have these mirror planes. You're not going to have any mirror planes in a chiral molecule in D5. So think about the operations that are in a D5H molecule and then just don't include the mirror planes, right? So that's the easiest thing to do. So I'll try to draw this pentagon with a little bit of perspective if I can. And then I'm going to define a z-axis and an x-axis and a y-axis. And then we can start thinking about our different operations. Of course, we're going to have a C5 spinning this pentagon, so interconverting all the sides of the pentagon. That's going to be our principal rotation axis. We have to think about, when deriving character tables, all the different operations of that point group. Of course, we're going to have identity. It's always going to be exists. We're going to have a C5, 72-degree rotation. We can do a C5 twice, 144-degree rotation. We can do C5 three times. We can do a C5 four times. We can't do a C5 five times because then we're back to a 360-degree rotation, which is identity. And then other than that, there's no mirror planes, but we are a D point group. So we're going to have perpendicular C2s, and we're going to have 5 perpendicular C2s. Why? We always have n perpendicular C2s, and we're a Dn point group here. Here we're D5. So we have 5 perpendicular C2s, and I'm going to draw one of them. It's going to go bisect the pentagon, but we're going to bisect, in 5 different ways through the 5 different vertices of the pentagon. That is a C2. I'll flip the pentagon like that. Right, it's going to take this point, go to there, this point, go to there, and it's not going to change this point or the central atom if we're talking about a molecule with a central atom. So we can call those C2, C2 prime, C2 double prime, C2 triple prime, and C2 quadruple prime. All right, well, now we have to organize these into classes. Identity is always in a class by itself. The C2s, the 5 perpendicular C2s, all those are going to be in the same class. We'll call it 5 C2s. They're all doing very similar things mathematically, so I think that makes sense. And then for the other ones, the C4, I'll use a different color here. The C5 and the C5-4 are going to be in a class. We'll call that the 2C5 class. And then the C5-2 and the C5-3 are going to be in their own class. We'll call that the 2C5-2 class. Now, why did I group these like this? Well, if you think about it for a little bit, I think it should make sense. And the reason is because let's say we're doing a C5 once, right? And we're keeping track of this point. That is taking this atom and moving into this atom. However, if we do a C5 now 4 times, that's taking this and going all the way around, okay? Now, what if we just define our axes different so that we're rotating the different way? Well, now a C5, oops, I didn't even put that. I did a C5-3, I'm sorry about that. C5-4 goes all the way around back here, C5-4. Now what happens if we just define things in a different way, right? If we do that and we rotate the other way, a C5 once goes to the same thing as a C5 4 did. And a C5 4 times goes the same thing as the C5 once did. So depending on how you define things, C5 and C5 4 are the same thing. Same idea with C5 2 and C5 3. Now, in the D point groups, the DM point groups, you can interconvert between axis systems that allow for this equivalency using the perpendicular C2s. That's why these are allowed to be in the same class. When you look at the CN point groups, these have to be separate classes. So in the CN groups, we don't have these perpendicular C2s, and we have all 5 of these operations on the top here that is circled are all in different point groups. We don't have these C2s that can interconvert these point groups. It's a subtle point. Mathematically, it can take some time to prove this. I've done that in some other videos, like on the C4 character table derivation video. But for here, either you'll be given I hope you'll be given information from your instructor about how to group these into classes, or you'll just have to look at these patterns, like the D's, they have these groupings with the C rotations because these C2s, D's have the C2s that can interconvert between them, whereas the CNs don't. Okay, but now that we got all this down, I think we can clear this and we can write the bones of our character table. And so by convention, we put the point group at the top left. And we have identity is our first column. We have our C5, but there's 2 of them, right? The C5 and the C5 4 times as our next character. You usually start with identity, and then always start with identity, this convention, and then the principal rotation axis. And we also have the 2C5 twice. And then we have the 5 perpendicular C2s. So we had 4 classes, and we had 10 total operations. 1 plus 2 plus 2 plus 5 is 10. We'll put a last column here just for functions that we may test. Because we have 4 classes, we've grouped them in 4 classes, we're going to have 4 irreducible representations. And for now, we don't know what the Mulliken symbols are for these irreducible representations. So I call them gamma 1, gamma 2, gamma 3, gamma 4. There's a rule that states that basically the number of rows has to equal the number of columns. So we have 4 classes, so that means we have 4 vectors or irreducible representations. The first one is always going to be the totally symmetric representation. So you just put 1s across the board. That's easy. Second thing to do is figure out these values under the dimensionality. I'm just calling them placeholders right now, A, B, and C. Dimensionality means just a fancy name for the column under E, the characters under the column of identity. And there's a rule, character table rule, that says, and again, look at my character table rule video for an explanation of all these different rules, that the sum of the squares of the dimensionalities, so in this case 1 squared plus a squared plus b squared plus c squared, has to equal the order of the point group. And the order of the point group is the total number of symmetry operations in that point group, which in this case is 10, right? 1 plus 2 plus 2 plus 5. And these values for dimensionality basically tell you how many functions transform together as that vector. So normally this is going to be equal to 1. It can only be equal to 1, 2, 3, 4, or 5. And most of the time, it's going to be 1 or 2s that you're going to get here. Only the really highly symmetric systems like tetrahedral and octahedral are going to get 3s, or icosahedral, you can get 4s. But basically think of 1s and 2s for the most part here. So what values can get us 1s and 2s? Well, the only way we can satisfy this equation if we have 3 1s and 2 2s. And nope, that's not right? Because that just doesn't add up to 10. It's going to have to be different. It's going to have to be 2 1s and 2 2s. That's going to be equal to 10. Okay, 1 squared plus 1 squared plus 2 squared plus 2 squared equals 10. So now we can put in 1, 2, and 2 into our dimensionalities. And I'm just going to erase this so that we have some more room as we work out some different aspects of this problem. All right, so at this stage, what do we do? Well, it's useful to plug in some functions. I always like to start out with z. So the z vector. So again, I'm going to have my x, y, and z here. Remember, your z is always going to be defined as your principal rotation axis. Your x and y can be defined however you want, but they have to be perpendicular to one another. Same with perpendicular to the z. And we're thinking about this z vector here, and we're asking, how does the function z transform with the different symmetry operations in each class? Well, identity takes z goes to z. So you think about a 1-by-1 matrix, and then you take the character across that matrix that, it's just a z times a matrix, a 1-by-1 matrix with a value of 1 is going to take you equal to z. You take the character of that, which we represent by chi, the Greek letter chi, and it's just the sum across the main diagonal. It's a 1-by-1 matrix, so it's just equal to 1. And so we know that the character now for the z function is going to have to be either gamma 1 or gamma 2. We're sort of hoping it transforms as gamma 2 just so that we can generate something new. Let's try C5. We can choose any operation in the C5 class. So we could do C5 or we could do C5 twice. What's going to happen here? Well, if we do a C5 on a Z vector, we're doing a rotation this way, but when we rotate that way, imagine taking a piece of string and rotating it this way, we're not really doing anything. The head, is still going to be pointing up, the tail is going to be on the down, so Z is going to go to Z, and for the exact same reason, we're going to get a character of C5 operation is going to be equal to 1. All right, what about the C5 twice? Again, not interesting. We're doing just 144-degree rotation, but again, that's going to be Z going to Z. And so the character is going to be of C5 twice operation is going to be equal to 1. Now, what about a C2? This is where maybe something will change, and it will. Z is actually going to go to negative Z here. Why is that? Because we're doing a rotation along one of these axes. We can choose it to be along the X. We can define that as one of our C2s. There's 5 perpendicular C2s. The next C2 is going to be somewhere like here that we're doing a rotation across, right? But that's going to be kind of a hard one to visualize. It's off axis. That's going to be 72 degrees off of what we defined our first one to be, which we defined for ease to be just along the x-axis. But that's going to spin this whole axis system down, and including with it the z vector. So z is going to go to negative z. And so now your matrix is going to be a value of -1, a 1-by-1 matrix with a value of 1, which takes z goes into negative z. You take the sum across the diagonals of the matrix. There's only one element. I'm doing this just to be rigorous because when we get to 2-by-2 matrices, then you'll see, we're going to do the exact same protocol. So right now it seems kind of stupid. Like, just tell me z goes to negative z. It's -1. Come on. But when we go to 2-by-2 matrices, we're going to have to do the math. So that's why I'm setting us up this way right now. So the C2 operation character is equal to -1. So that's kind of cool. That actually got us something different than gamma 1. And so that's going to be the z vector. Now we could have predicted that because we know these things have to be orthogonal to one another. That's one of our other character table rules. So gamma 1 dotted with gamma 2 has to be equal to 0. And so if we look at these two vectors, gamma 1, right, dotted with 1, 1, 1, -1, what we just figured out, that's going to be equal to, that's actually not equal to 0 right now. We have to, when we're talking about these dot products, we have to adjust it to take into account the number of symmetry operations in each class. So we have 1, 2, 2, 5 symmetry operations in each class. So one of these vectors, that's why I left space here on this first vector, I'm going to multiply by a 1 and a 2. This 2 came from up here. And a 2, this 2 came from up here. And then lastly, a 5. And so that's going to get us what? 1, this is basically 1, 2, 2, 5, dotted with 1, 1, 1, -1. And that, just to remember your dot product rules, right, is 1 times 1 plus 2 times 1, second terms, third terms, 2 times 1 plus -1 times 5, and that all equals to 0. So it checks out right. We could have used that principle to just, puzzle this out, but it was kind of nice to see how this worked with the z function. And we also, as a bonus, got to figure out how the z function transforms. So that's kind of nice. So at this stage, I'm going to erase a bunch of stuff, and we are now going to go in and think about our next function to transform. These next ones are going to be where the math gets a little more complicated because we're going to have 72-degree rotation. So I think I'm going to need even more space for all of these. So I'm just going to erase them as well. And so, let's think about x, right? So let's think about an x vector. So I can write an x vector here. We're imagining this little x vector. And just like last time with what we did with z, we're going to go through all these different operations, one operation in each class. We can choose any operation we want in each of those classes. It doesn't matter, mathematically the same. That's sort of why they're in the same class in the first place. It is why they're in the same class in the first place. So we do an identity on x and we get x. And now I'm going to go right ahead and do the C5. And when we do a C5, we're doing a rotation, right? 72-degree rotation. X is going to go into something like this, right? It's not going to quite get to Y because it's only 72-degree rotation, not a 90-degree rotation. So this is where things get complicated, and we have to use trigonometry to help us. We have to use a 2x2 rotation matrix, and that's going to be cosine 2 pi over 5. You can do it in radians or degrees. Here I'm doing radians. 2 pi over 5, right? 2 pi is 360-degree rotation divided by 5. That gets us 72 degrees. Minus sine 2 pi over 5. And our y is going to be sine 2 pi over 5. And our other one component element of the matrix is cosine 2 pi over 5. And so what ends up happening here is now you see that x is transforming as a combination of x and y. They transform together. You can't describe x without also describing x with y. And same thing with y. And so your character here is going to be the trace of the matrix, which is why I kept doing the 1-by-1 matrices before. It's going to be cosine 2 pi over 5 plus cosine 2 pi over 5. For simplicity at this stage, we're just going to call that 2 times cosine 2 pi over 5. Now, cosine 2 pi over 5 is 1/4 times square root of 5 minus 1. You could write it out like that. Most character tables won't, so they'll just write it out like this. And so in here, that's going to be our character. So this is a non-integer character, right? You can have non-integer characters in character tables. That's totally fine. What happened with identity? Well, identity has x and y going together. We're forced to keep them together. These functions transform together. So we have the identity matrix, one's across the diagonal, takes xy, goes into xy. And we take the trace of this matrix, and it's 1 plus 1, which gives us 2. Chi, our character for the identity, equals 1 plus 1, which equals 2. That's why we had a 2 there. So that makes sense. Okay, so now we're ready to do our C5 twice. So for our C5 twice, we now are talking about a 144-degree rotation. And so instead of cosine 2 pi over 5, we have to do 2 times more of that rotation. So it's going to be cosine 4 pi over 5. But everything else about this matrix is going to be the same. We have the minus sign element here. We have the positive sign element here, 4 pi over 5. And we have cosine 4 pi over 5. We take the trace of this matrix, and we're going to get cosine 4 pi over 5 plus cosine 4 pi over 5. And we're just going to call that 2 cosine 4 pi over 5. So that's going to be our character. Again, another non-integer character for 2 cosine 4 pi over 5. Last one is going to be our perpendicular C2. Well, let's choose that perpendicular C2 we were talking about earlier that was just running right along the x-axis, right? So we're going to be rotating it this way. So x in that case is just going to go to x. We're along the plane there. We're along the x-axis there, so it doesn't do anything. Y, however, if we have a y vector, that's going to now be spun by rotating across the x into negative y, sorry, negative of itself. So x went to x, y went to y, and so the 2 by 2 matrix, now we have to do 2 by 2 matrix because these, again, these x and y functions are going together. We're going to get 1, 0, 0, negative 1. That's the matrix by matrix multiplication that takes x, y into positive x and negative y. We take the trace of that matrix, and we get our character being equal to 0, right? 1 plus negative 1. So we did that component here. All right, and so at this point, it's good to just test some other functions. You could try to use orthogonality here to help you. You can see that these functions are going to be orthogonal, like gamma 2 and gamma 3 are orthogonal. 2 times 1 is 2. Okay, fine, I have a 2 there. And then, is it going to be orthogonal? You have to work through some crazy algebra to, you have to expand out what cosine 2 pi or 5 is. It will end up being orthogonal. So it gets tricky just staring at this and trying to figure out what's orthogonal, like I showed you after the fact with z. So let's try another function. That's our best hope for getting this last gamma 4, the characters for gamma 4. So let's try x times y. We can do quadratics. Okay, and at this point, I'm going to write down here what are, we have to do some erasing because we're going to need some more space. And so what we're going to have to remember if we're thinking about xy transforming, I mean, for identity, it's going to be easy, right? xy is just going to go to xy. But then it's going to get crazy once we do this for the C5 rotation. And we have to keep track of these different elements. So I'm going to, just for now, and later we'll erase it when we don't need it, but I'm going to keep these rotation matrices so that we have them ready to go. And I'm going to write out. So first, let's just write out for identity. We know that one's simple. So this is identity. xy just goes to xy. No problem. We're going to need to keep track of what happens to x when we do a C5, and then eventually for a C5 too, but we know that that's the same with just 4 pi over 5 everywhere. So I'm going to erase that one too, again, just to give us some more space. All right, so I'm going to write this, I'm going to expand out this matrix multiplication. So what is this saying? It's saying x is going to be going to cosine 2 pi over 5 times x minus sine 2 pi over 5 times y, and y goes to sine 2 pi over 5 times x plus cosine 2 pi over 5y. That's just going to be helpful for us to have that written down. So now I can erase this, and you'll see why hopefully in a second. And to give just even more space, I'm going to move myself up over here, temporarily blocking our character table. Okay, xy. This was for E. That was identity operation. Now, let's do it for C5 operation. What is xy going to go into? It's going to go into these two things times by one another, right? X times y. So that's what we have to now FOIL out. Okay, so we're going to have cosine times cosine terms, cosine squared 2 pi over 5 xy. We have 4 different terms here. We're going to have sine terms, minus sine squared 2 pi over 5 xy. And then we can do the 2 y terms. So that is going to be a minus sine 2 pi 5 over 5y cosine 2 pi over 5x y. Sine 2 pi 5, sine 2 pi over 5y times cosine 2 pi over 5y gives us sine 2 pi over 5 times cosine 2 pi over 5y squared. And then our 2 x terms plus sine 2 pi over 5 times cosine 2 pi over 5 x squared. Now, what's pretty interesting about this is if you do this, you notice something. We have xy terms and we have x squared and y squared, and they're minus. Now, some of our d orbitals functions are xy, and another d orbital function is x squared minus y squared. What this is telling us is that these two functions transform together. You can see at the end, that's what we're going to get. They transform together. Meaning, just like x and y were linked together, x squared and y squared are linked together. We can't describe how xy transforms under the C5 operation, and therefore all the operations are linked together. We want one vector for this, without also describing how x squared minus y squared transforms. So we can factor out these components. And so that's what I'm going to do. I'm going to factor out the xy, cosine squared 2 pi over 5 minus sine squared 2 pi over 5 plus x squared minus y squared times sine 2 pi over 5 cosine 2 pi over 5. And that is looking correct. So now we got to do, well, there's a few things we can do now. What we have to do now is we know that the character here, x and y and x squared minus y squared go together. So x squared minus y squared under identity has to be in this portion too. And so we're going to have a 2 by 2 matrix. All these are going to have 2 by 2 matrices. So for identity, that's the identity matrix. It takes xy and x squared minus y squared and goes into xy and x squared minus y squared. And then we take the trace of the matrix, and that gets us chi equals 2, right, for identity. We have to do the same thing for C5, but we're not there yet because we just figured out how xy transformed. We didn't figure out how x squared minus y squared transforms. A lot of math. So we're going to square this term. I'm not going to rewrite it, but it's going to be this term squared minus this term squared. So I got to FOIL out this term squared. So I'm going to have cosine squared 2 pi over 5x squared. And then this term is going to times itself, sine squared 2 pi over 5y squared. And then I'm going to have this term times that term times 2 because they're the same. And so those are a negative times a positive. So it's minus 2 cosine 2 pi over 5 times sine 2 pi over 5 times xy. All right, that's just the x squared portion of this. We just did x squared. Now we have to do y squared and then the minus of that. So again, we have to envision squaring this term. So we have to FOIL it out. We're going to get 3 terms again. And we have to add a minus sign. So we add a minus sign. We square that first term. Sine squared 2 pi over 5 x squared. And then this one squared, a minus sign, remember? Cosine squared 2 pi over 5 y squared. And then this combination, minus 2 cosine 2 pi over 5 sine 2 pi over 5. And it's x times y. All right. So now we want to combine like terms and think of it in that way. Well, we have cosine squared 2 pi over 5 x squared, and we have sine squared 2 pi over 5, right? And so we also have this 4 cosine 2 pi over 5. This 2 cosine squared, these two terms, this term and this term are the same. So that's going to get us what? Negative 4. Let's do that one first. That one's easier. Negative 4 cosine 2 pi over 5 sine 2 pi over 5 x y. Okay. And then we're going to get these other terms, which are right here. So what we're going to attempt to do is factor out these things in terms of x squared minus y squared. That's what we're trying to do. And so we have here an x squared. But the thing is that this is actually turning into, we have to combine some terms here. So we're going to end up with at this point it's getting fairly complicated, and we're trying to get x squared minus y squared here. And so what we have to do, so we have to take advantage of either one of two things. One, we could use the definitions that I told you or alluded to earlier about that involve square roots of 5 for these cosine 2 pi over 5s, and we could, get everything into that mode. A simpler way is just to take advantage of some relationships here that are known with these cosine 2 pi over 5 things, kind of esoteric ones, but I'll write them maybe in green somewhere where I can find space. Let's see. Cosine squared of 2 pi over 5 minus sine squared of 2 pi over 5 is actually equal to cosine 4 pi over 5. Okay. And the opposite of that, the negative of that, right, is just going to be the negative of this. So if we look in here, we have cosine squared 2 pi over 5 x squared, and we have sine squared 2 pi over 5 x squared. So we have that times x squared. So that is actually just going to be equal to cosine 4 pi over 5. And so that part of it works. And then we have the negative of it too. So if we think about taking the negative of all this, so a negative sign there, a positive sign there, and a negative sign there, right? We have that as well for y squared. We have a positive sine squared 2 pi over 5 terms for y squared, and we have a negative cosine 2 pi over 5 y squared. So it's amazing how the math all works out on this stuff, but this is how you can factor it out, right? And so now you have x squared minus y squared in terms of xy and x squared minus y squared. Again, what we expected because we were noticing up here earlier on when we applied this to xy, that xy and x squared minus y squared transform to one another. So it's getting a little bit messy here. I apologize for that. But what we're going to end up having is a transformation matrix for xy and x squared minus y squared. And really the only elements we care about are the on element diagonals. I mean, I could write the whole 4 by 4 matrix, but just to save us a little bit of space here, we only care about these ones that are on the diagonal, right? And so that's the term that takes xy into something times itself. And what is that? Well, that was cosine squared 2 pi over 5 minus sine 2 pi over 5, which we just said before was equal to cosine 4 pi over 5. And then same thing with the x squared minus y squared. So xy squared minus y squared, the on diagonal component is the part that factored out as itself, which was also cosine 4 pi over 5. And so then you take the trace of this matrix and it's just cosine 4 pi over 5 plus cosine 4 pi over 5. And so your character here is 2 times cosine pi over 4 pi over 5. Okay? And so for the C5-2, we're going to get the exact same math. All the exact same math, because remember, all these 2 pi's, the only difference is all these 2 pi's became 4 pi's. Okay? And the same relationships hold. So this relationship that I wrote for you here, now if you swap the 4 pi's, okay, it's just how the trigonometry works on the unit circle, the 4 pi's for the 2 pi's, so cosine squared 4 pi over 5 minus sine squared 4 pi over 5 is going to equal cosine 2 pi over 5. And so all the 4 pi's are going to become 2 pi's, and all the 2 pi's are going to become 4 pi's. And so basically what's going to happen is we don't have to rewrite any of this, thank goodness, but C5-2, right, our transformation matrix xy, x is going to go to cosine 4 pi over 5x minus sine 4 pi over y, right? 4 pi there. And all this is going to come out exactly the same. And what you're going to end up with here is a 2 pi here. I mean, there's no real point in writing this off because it ends up the same thing. And so, you know, sort of cool how the math works there. Once you do it once, there's no real need to work through it again. You're going to get a cosine 2 pi over 5. Now, just for the last one is going to be our C2s. So perpendicular C2s. Our perpendicular C2s, we got to think about. And so what happens to xy? Well, we might need to refresh our memories since it was way earlier in the video that we talked about xy and the perpendicular C2s. We defined one of our C2s, so our x vector is like this, let's say, and our y vector is in green. And we defined one of our perpendicular C2s as going along the x. So x went to x and y went to negative y. So that means x went to x and y went to negative y, which equals negative xy. So, but we know x squared minus y squared has to also be considered because these two functions transform together. X went to x, so it went to x squared minus, quantity minus y squared. And so that is x squared minus y squared. And so our matrix here, our 2 by 2 matrix, xy, x squared minus y squared, that matches this or explains this transformation is going to be a negative 1, a 0, 0, 1. take the trace over the matrix, and your chi, your character for C2 operation is -1 plus 1, which of course equals 0. And so that gets us a 0 here. So we derived the character table. The only thing left that we have to do is we have to put in the Mulliken symbols. And so how do our Mulliken symbols work here? Well, just like always, we think about, we call these E's because they have a dimensionality of 2. It's Mulliken symbol rules. Dimensionality just means the character under the identity character. Remember, these E's are not the same as this E, which is unfortunate that those are named the same thing. And then for dimensionalities of 1, we put A's or B's. If we're symmetric with the principal rotation axis, we call it an A. If we're anti-symmetric, we'll call it B. This is the principal rotation axis to C5. We're both positives here, so we give it 1s. And then we just look for like perpendicular C2s is the next thing we usually look for. It's the only other thing that distinguishes it themselves. There's 1s here. So if we're symmetric with the C2, we give it a 1. If we're anti-symmetric, we give it a 2. And here, there's no real well-defined rules for Mulliken symbols. We just arbitrarily call one of these 1s and 2s. Probably there's some books somewhere that are published with this reverse. Doesn't really matter, but you have to make sure that you don't make a mistake when you're doing some homework problems or something like that, that you're using whatever language that the people want you to be using that way. But you can see we matched that. We figured out how x squared minus y squared and xy transform that helped us derive E2. We figured out xy helped us derive E1. These other functions are much more complicated, but could be derived using similar trigonometric principles.